Hey guys, so this week we looked at thermal physics and we started off by looking at specific heat capacity. And what we were interested in was what temperature change, so delta theta, do we get when we input some thermal energy into a material. So our thermal energy in this case, as we said, was delta E. And this was actually carried out by James Joule, and as we discussed, he discovered there were three proportional relationships. So that change in temperature was proportional to the change in energy, which makes sense. If you supply more thermal energy, obviously you're going to get a greater change in temperature. That makes a load of sense. It's also inversely proportional to the mass of the object you're heating. Again, that makes sense. Fans of the Great British Bake Off, you'll know if you put a big cake in the oven, you have to cook it for longer. And the final thing was it was inversely proportional to some intrinsic property of that material, and we call that the specific heat, or specific heat capacity, SHC. And what we did in lesson was we shoved those three together and we arrived at the equation delta E, the change in thermal energy, is equal to its mass times its specific heat times its change in temperature. So we can work either way there. We can calculate a temperature rise or fall given an amount of thermal energy change, or we can go backwards and calculate the thermal energy required for a given change. One thing we didn't look at actually was that this equation here is a sort of time-dependent version, if you like. So this is when we change things. We can also talk about the sort of total thermal energy in a system or in a material of mass m, specific heat capacity c, at a temperature at a given time, theta. So we didn't talk about that, but there are actually two ways that we can look at this. So there are equations, and we were actually more interested in examples like this. So what happens when we take something hot, so body A here, that could be a cannonball or a red hot nickel ball, like the videos I showed you, and we drop that in something colder. So here are our two bodies. Our hot cannonball starts off with an initial temperature, theta A. It's got its own specific heat capacity, which may be distinct and different from the other body. So water will have its own specific heat capacity, and it has its own mass, m subscript A. So all of these can be different. We want to know if we drop this in and we wait long enough, actually this whole system is going to come to thermal equilibrium. And we ask the question, how can we calculate this? So basically what we need to do is make some assumptions, as always. And the assumption we made was we're going to consider that this whole system is closed. So this is a closed system, and that means that no energy enters or leaves. So actually what we're saying here is that the total amount of energy given up from one body, so subscript A here, the ball, because it's a closed system, we can say that any heat that loses is going to be given to the other body, to the water. So actually this is going to lose heat, so I'll put a negative sign there, and it's going to be given to the body of water, so that's going to have a positive temperature rise. I'll just put the plus in there just to make that completely clear. So this is a great starting point now. All of our thermal energy from one body is going to the other, and we have this equation here which we can use. So all I'm going to do now is substitute in some values. So we know that for body A, we have minus now m subscript A, c subscript A, and then instead of delta theta, what I'm going to do is I'm going to break that down. So we're going to assume some final temperature theta, as we've got over here, minus the initial temperature theta A. And I'm going to do the same for the other side. Here I've got a positive symbol, so we don't need that negative sign. And that's the mass, the specific heat, and again the same final temperature but a different initial temperature. And now this basically becomes a simple algebraic problem. Just move this over here. And the first thing we want to do obviously is expand the brackets every single time. So we're going to do those. By the way, closed system, I should write up here, just while I'm thinking, that implies conservation. It's a conservation law, it's conservation of energy in this case, which is what we're saying here in this statement. Just make that a bit more clear. And we'll see that a lot more in physics with other conservation laws. You will spot something similar here, mathematicians, if you did mechanics, when we get to the final line. So, digressing, moving on. I'm going to expand these brackets, so that's going to be minus the mass, the specific heat, and the final temperature, minus minus, so plus the same mass, specific heat, and the initial temperature for body A, the ball, and do the same on the other side, minus MB, CB, theta B. And really what we're interested in is theta. We want to know theta, so I'm going to basically collect terms, really. So I'm going to add this term to the side, and I'm going to add this term to the side, so adding both terms to both sides. So that will give me MA CA theta A from here, plus this term over here, so MB CB theta B, and that's going to be equal to, this term is going to be carried over by adding to both sides, that's the final temperature, plus this term which remains on this side. And now I can collect terms, so again we're interested in only the final temperature, so that's going to be theta, and I can collect terms MA CA, so I've just pulled out a common factor, MB CB. This side of the equation remains the same, so the final step then is just to divide both sides by this term, which will give me the final answer of theta is equal to MA CA theta A plus MB CB theta B, all divided by this term, so the mass multiplied by the specific heat of each in addition to each other. So that's our final equation. That's the equation we got to about halfway through lesson 1. So this tells us what our final temperature theta is of a mixture of two bodies that start at potentially different masses, specific heats and temperatures. Now what we can do with this, there's something more interesting here. If we actually look at this, if I just highlight a few bits, if we look at this and we look at this, so actually they're just two products of mass, specific heat and temperatures for the two distinct bodies. Each term has the same subscript. So if I go back up to the top here and just highlight this, they have the same form. So basically what we're saying here is, if I write this again, our numerator in this case is just the total energy, thermal energy in body A initially, plus the total energy of body B. Okay, that makes sense. I'm going to leave the bottom, so that will remain the same. And again, if we look closely, actually what we've got is a sum. We've got a sum over however many bodies are present in our problem. So really, I can rewrite this as a sum in this sense. So actually, we've been adding two bodies. We could do this for n bodies if we like. You'll never get anything more than two bodies in your mixture in an exam, but hopefully this sort of shows you basically the physics that's going on. Your final temperature here is just the sum of all the initial energies weighted by each body's mass and specific heat. So it's a weighted sum. Again, mathematicians, if you do mechanics, you will probably have come across equations of this form before. Okay, so we have this, and I'm gonna cut this out. And we had a question in lesson 1, so we'll talk about question 5, and this question is about dropping cannonballs into bathtubs. And we want to know if, so our cannonball here is 1000 degrees C. We were interested in, well, what happens to our 5 kilogram 1000 degrees C cannonball when we drop it into 10 kilograms of water at roughly room temperature. And we want to know, can we make a cup of tea? So, you know, in physics we always do the important questions. So what I'm going to do is I'm going to put this together, use the same approach as last time. If this was an exam question, the first thing I would do really is say that we are assuming conservation of energy. Because we're assuming conservation of energy, that means that the total amount of energy is going to be the same. Therefore, we have this equation. So theta, we have two bodies, so the mass and specific heat of the bathtub, the water, multiplied by its initial temperature, plus the mass of the steel ball, specific heat capacity and temperature of the steel ball, all divided by that weighted mean, if you like, underneath. So that's going to be MWCW plus MSCS, so the sum of the product of their masses and individual specific heat capacities. So basically all I've done is I've used this equation here. So now I can substitute in some numbers. So my mass is 5 kilograms. Okay, remember to look out for SI units here. The specific heat of, I should write this up here actually, the specific heat of our two bodies, so we have 419 and 4.2 times 10 to the 3. Both of those are in joules per kilogram per Kelvin, remember? So that's 419 multiplied by the initial temperature again in degrees C. This so this is in degrees C, yeah, 1000, and I'm going to put that in brackets. Remember, always put stuff in brackets. If you're going to be putting stuff into your calculator in one go, it's always a good idea. Hedge your bets, put them in brackets, you won't slip up. So that's multiplied by the mass of my water, multiplied by its specific heat capacity, so that's 4.2, my bad, times 10 to the 3. Again, this is in calculators, I put that in its own set of brackets just to be safe, multiplied by its initial temperature, and again, divided by the sum of the masses times the specific heats. That's 10 times 4.2 times 10 to the 3 there. And what we can do is we can plug this into your calculator, and you should get, if you do this correctly, you should get an answer. So let's actually do it. So 5 times 419 times 1000, I'm going to add that to 10 times 4.2 times 10 to the 3 in brackets, remember, times the initial temperature 25. I'm going to divide all that by 5 multiplied by specific heat 419 for steel plus 10 kilograms multiplied by the specific heat for water. Remember, put that in brackets as well. And putting all that in, you should arrive at the answer roughly 71 degrees C. So to answer the question, that is roughly, we're about 10 degrees short, so it might be a weak cup of tea, but you could make a cup of tea out of that. In a few weeks' time, actually, what we'll look at is a similar problem. Can you make a cup of tea on a mountain? And we'll see what happens there as well. So you can put a nickel ball, 5 kilogram cannonball in a bathtub at 1000 degrees C, so near melting point, and you probably can use that water to make a reasonably decent cup of tea. Might not taste too good though. Okay, see you later guys.